AP Calculus AB, Unit 9, Day 6, Lesson, Mean Value Theorem. Now, we've talked about Mean Value Theorem before, but we're going to talk about it in a new way today. So, we've talked about Mean Value Theorem as the average rate of change, the average slope, and that's like average derivative. So, we could review that real quick. There's a couple of requirements to use it. It has to be continuous on a closed interval and differentiable on an open interval. Average rate of change will just be the slope of the secant line connecting the two endpoints. It's a really simple idea. You have all these infinite different slopes, but really the average of all of those will just be the slope of the line connecting it. So that's one part of it. The other part of it is that there's this guarantee that there must be at least one point, which they refer to as C, where the actual slope of the curve equals the average slope. So on this picture right here, you can tell, like here, the tangent lines are parallel to that line. So there's two of them. And they call these values C. They have to be in between the endpoints, and that's something that you're asked to find a lot. So this is what we covered already, but we're going to talk about mean value theorem not for slopes anymore, but for any function, which, by the way, could include slopes because slopes are functions. So we're going to say the mean value theorem for any function. And you could kind of try and apply this to some sort of like real life example, like what's your average rate of all time? You're like, well, maybe it's like 100 pounds, and this is how much you weighed at the beginning, and this is how much you weighed at the end, and this is all the weights in between. Now, the average height of this curve, average y value, would be the average of the function. So that's what we're trying to find now. What's the average y value? Okay. And, is it going to be exactly in the middle of the beginning and end weight? No, not necessarily. But there's this other idea that the average, you're going to have at least one time equal to that, and they call that the C value. Okay. Now I might refer to it as like X star because I don't know if the book uses X star just to kind of differentiate it from the other one. But here's the dilemma. How do we find the average y value? It seems like a pretty simple idea, but how do we find it? Okay. And so, in going back to the weight thing, your average weight, you had to weigh your average weight at least once. There's no way you skipped it, right? I mean, at least one time. So it's kind of logical. I like to kind of use a three-dimensional sort of idea to kind of think of how we approach this. So imagine you have a measuring cup of flour. And, if you're like me, I'm really all about following the directions and putting the exact amount. So when I scoop it in, it's usually like too much. And so I scrape off the top, or maybe it's one of those bigger measuring cups where it has all the different levels. And so I like shake it, kind of like try and level it out to make sure it equals the right height. Now, we have a bunch of flour in the cup that's all lumpy and not leveled out. But then when we level it out, it's the same amount of flour. It's just going to be all nice and kind of, smooth and flat. We haven't added or taken away any flour. We've just kind of rearranged it. And the height of that, by the way, is the average of that original lumpy height. And so we're going to use that approach. So what I want to say is like the area under the curve is like the flour in the measuring cup. Okay. And if we level it out, if we flatten it out, it's going to be the area of a rectangle now. Same area, right? This is the same area that was under the original curve. Okay, so we're going to get the area of a rectangle. Now, to find the area of a rectangle, you do base times height, right? For us, now, by the way, the area under the curve, which is also the area of the rectangle, we could get from integrating the original function, right? We're going to integrate the original function. That would give us the area under the original curve, which is also the area of the rectangle. Now, the base of the rectangle is going to be this right here. This is the base of the rectangle, and it's always going to be the right limit minus the left limit. That's just the distance between those. So that's going to be b minus a. The height of our rectangle is f average, right? And so now we could solve for f average by dividing both sides by the base. And that gives us the formula for the mean value theorem, the mean value of a function. It's 1 over b minus a, integrate a to b of the function dx. I personally wouldn't memorize it because I guarantee you'll mess it up. Back when I was teaching this the first year, I kept messing up because I tried to memorize it. I kept confusing it with like fundamental theorem of calculus, which it kind of looks like, but it has nothing to do with. I just think always go back to this idea. Okay, it's the area under the curve flattened out, divide by the base to get the height. That's it. It's a rectangle, divide by the base, the height is what you want. This is the area of the rectangle, area under the curve, divided by the base of the rectangle, use the height of the rectangle. Simple. The other part says there must exist at least one point C where the actual value equals the average value that we get from this formula. And so you're often going to be asked to find that. Okay, there might be more than one. These ones can actually be on the endpoints because it's not a derivative issue. Now, our book uses X star instead of C, just so you know, just so you understand what they mean. Okay. Now, here's the thing. We can use this for any kind of function. We could use this for average velocity. We could say, okay, well, let's integrate the velocity to find the area under the velocity curve from A to B. Think of it as being leveled out by it like a rectangle. Divide by the base of the rectangle, and you get the right answer. In fact, let's just think about it. What's the antiderivative of velocity? It's position. And then you plug the top in, and you plug the bottom in, and then you would get SB minus SA over B minus A, which is the way we've been calculating average velocity forever. So this approach works. We could use it for average slope, which that's what velocity is. We could say, what's the average of f prime? Well, f prime has a function, so we could integrate the function and find the area under it from A to B. Think of it as being leveled out like a rectangle. Divide by the base of the rectangle, and you get the height. Now, guess what? This is going to totally make sense because what's the antiderivative of f prime? F, and you plug the limits in, right? And if we just took this one more step, look what we have. We have the same formula we've been using. Now, if it is a derivative, this formula is way faster to use because you just start with it right away instead of doing all this extra work to get to it. So I think it's worth it to have that other version that just works for derivatives because it's going to be a lot faster. But this one works for everything, okay? So we're going to let's do a couple examples on the back here. Now, it does have to satisfy the conditions. So, here's just a quick example, and we'll draw a graph to just kind of think about it. So this is a really simple parabola. And I'm going to go and graph it. Really simple parabola. Okay? And I'm saying find the average value from 3 to 6. So from 3 to 6, what's the average value? And I mean, it's got to be somewhere in here. Is it exactly in the middle? Probably not, Like, what's the value here? This is going to be 636, and this is going to be 39. The difference between these is 27, cut in half, 13 and a half. Is it 22 and a half? Probably not. Okay, and the graph is getting steeper, so I bet it's going to be down here lower, or no, probably above it, probably above 22.5. Well, or below it, because it's getting steeper. So it's going up quicker. So there was a lot more values down here lower. Yeah. Okay. All right. So how do we calculate it? Well, let's just do F average. And we said it's going to be the area under the curve, 3 to 6. Then we're going to divide by the base of the rectangle, smooth out rectangle. It's going to be 1/3. The antiderivative is x cubed over 3. So that's going to be 1/3. If you plug 6 in, it's going to be 36. It's going to be 72 minus 9. It's going to be 1/3 of 63. So it's going to be 21. So it wasn't 22.5, but it was probably close. I mean, you should have a basic idea of like where it should be. If you get a totally wrong answer, it should stick out to you if you're thinking about it. So that's F average. Part B says to find all the values of C. So that's where the actual function equals the average, the average. So the actual function we had is x squared equals the average is 21. We're going to take the square root of both sides. Plus or minus better be in your work. Okay, but we only want the ones that are between or on the endpoints. So we just want positive 21. Now, is that between 3 and 6? I mean, just you could estimate it just to make sure it makes sense. 21 is between 16 and 25. It's close to 25, so it's probably like, 4.6 or something like that. Right? The calculator says it's 4.583. 4.6 is pretty good answer. So that's the idea. Okay. On today's assignment, number 7, this is the problem, or this might help you on that problem. Average position. Well, if you want F average in general, mean value theorem, you're going to integrate the function from left to right, and then you're going to divide by the base of the rectangle. Now, if you're like, is it a minus b or b minus a? It's smallest to biggest, left to right, and then here you want to do bigger minus smaller. This should always be positive. We could use this idea for average position. We could just plug position in, right? We could use it for average velocity, which I showed on the front, which, by the way, does break down into SB minus SA over B minus A, which I would probably use that instead. We could use this for average acceleration. Integrate the acceleration, find the area under it, smooth it out like a rectangle, divide by the base of the rectangle, but this would also be VB minus VA over B minus A. Anyways, keep that in mind for problem 7. Also, you might, use our calculator for some problems. These are some problems that we were doing before, a couple assignments ago, fundamental theorem of calculus part 1. And this is where I know a function, I want another one, and I have the derivative that I may or may not be able to integrate, but if I'm allowed to use a calculator, you should want to use a calculator. So we start with the fundamental theorem of calculus. We say, okay, I don't memorize this. I'm like, okay, if I integrate the derivative, I'm going to get the original function, right? Of course, right? Then I want 10, I have 18. Smaller on the bottom, bigger on the top, whichever one. And so that's what I'm going to do next is I'm going to plug these in. This is what I'm looking for. So if I add this and subtract this over here, I get f of 10 equals f of 18 minus the integral of 10 to 18 of f prime of x dx. Right? And we have f of 18 is 150. And we have f prime is x squared natural log of x. This is fundamental theorem of calculus part 1. Now I can do this on my calculator. This is going to be helpful for a couple problems on tonight. Let's review. I can totally do this on my calculator. 150 minus math 9 x squared natural log of x, comma 10, comma 18. I can do this all in one calculation right there. That's the answer. Done. F of 10 equals negative 4164.465. Rounded or truncate comes out the same this time. I always truncate. It's hard to mess up truncating. So we're using the fundamental theorem of calculus, part 1, FTC, right? Part 1 says if you integrate f prime, you get the original function. If you got limits, you plug limits in next. It's kind of a basic idea that, like, if you don't understand that, like, I don't really know how you've been thinking about integrals this whole time. Now, we could use the same idea in sort of a different kind of problem. And I guarantee you can have problems like this on your next test. On this one, I'm going to say, okay, well, I know f12 is 50, and I want to know f6. And this is the graph of the derivative. Now, I'm using the same approach. I'm going to say, okay, well, let's integrate the derivative from 6 to 12. And that should give us f12 minus f6. And this is what I want. So I could add this over here, subtract this over here. So f6, I'm going to rewrite this. f6 equals f12 minus the integral 6 to 12 of f prime of x dx. Exact same strategy as the last problems. Here's the difference. How do I find this? Not on a calculator this time, but we're going to use the graph. The integral of the derivative is the area under this graph. So we're really just trying to find this area right here. That's what's going to go right there. f12 is 50. And the area of this graph, I mean, you could do a trapezoid or you could do a rectangle and a triangle. The base is 4, the height is 6, this is 24. Base is 2, the height is 6, 1/2 base times height is 6. It's going to be 30. And so f of 6 equals 20. Same idea, little different way of finding the integral of the derivative, geometrically instead. Okay, so this is today's assignment, F6 worksheet. So try it out and let's get good at this new mean value theorem. Try not to just memorize it. Try to think it through. You'll remember it longer, better, and you'll understand it. You'll make less mistakes with it.